Okay, so I want to go back to this problem of this Hamiltonian involving the dot product of our two spin operators for our two spin 1f particles. And we solved this problem. We found the eigenvectors and eigenvalues. And after that, we found that those vectors that we found happened to be states of total angular momentum and total z component of the angular momentum. And it's not obvious that why that's the case just looking at this expression in our Hamiltonian. So a way that we can see why that would be the case is to do a little trickery. And it looks a little weird the first time you do it, but it's kind of the standard thing you do whenever you have this kind of a dot product of these two spin operators. We can define a total spin operator as just being the sum of our individual spin operators. And these are all vector operators. And then we can compute s squared. So a vector squared is just dot product with itself. So we have s1 plus s2 dot s1 plus s2. And if I FOIL this, I get s1 squared plus 2s1 dot s2 plus s2 squared. And now I can solve this for s1 dot s2. And so we see that we can rewrite this operator in terms of the total angular momentum operator squared. So now at least it makes a little more sense why are the eigenvectors or eigenstates of this operator were corresponded to states of definite total angular momentum and total z component of angular momentum. And now that we've rewritten our operator like this, we can solve our problem much more easily by because we know we can expand our state vector in terms of our, the eigenvectors we found before, and then we know how the Hamiltonian will act on them, or, well, we'll try and work out how the Hamiltonian acts on them. So the Hamiltonian acting on our 1,1 state, we have this. And naively, what you would do is, well, the total spin of this state is 1, or, well, h bar. So I should just replace my s squared with h bar squared. And we're dealing with two spin 1f particles, so s1 is just going to be h bar over 2, and s2 is also h bar over 2. So s1 and s2 squared are just going to be h bar squared over 4. And if you calculate that out, what you get is this. So we see that this is telling us that this state is an eigenvector of this Hamiltonian with eigenvalue alpha h bar squared over 4. And this is exactly what we found last time when we did it with the all the matrix stuff. So far everything is consistent. Similarly, we could do the same thing with these other two states with total angular momentum 1 and the various z component of the spin, different z component values. And the calculation would be exactly the same because this Hamiltonian doesn't depend on the m value, doesn't depend on the z component of the spin, it only depends on the total spin of the system and the spin of the individual components, which is the same for each of these states. So the calculation would be exactly the same, so we would expect to get the same eigenvalue. And again, this is exactly what we found before. All three of these states did have eigenvalue of alpha h bar squared over 4, which we called alpha prime last time. But the problem is, when we try and do this with the last state, with the 0, 0 state, when you work it out, you get the wrong eigenvalue. So last time we found that the eigenvalue was minus 3 alpha h bar squared over 4. But when we do things this way, we get just minus alpha h bar squared over 4. As it turns out, the reason for that is that these eigenvalues are not correct. So s squared acting on this state does not give me h bar squared. Instead, the way it works is this. So s squared acting on a state of total angular momentum and z component of angular momentum will give me s times s plus 1 times h bar squared, rather than just s times h bar squared. S times h bar all squared, I mean. So I'm not going to get into why that is, but that's the thing that is wrong. And it's unfortunate that it happens to be the case that when we do things the wrong way, we get the correct eigenvalue, and it's just a coincidence that we get the same value doing things the wrong way. So we can rework things using these eigenvalues. And if you do that, what you will get are, so for this state, s is 1. So I'll have s, 1 plus 1 is 2 times 1 is 2. So I should get a 2h bar squared. And then my S1 squared operators, they act in the same kind of way. So rather than just getting a h bar over 2 squared, what I have is 1/2 plus 1, which is 3/2, times 1/2, which is 3/4. So I get a 3/4 h bar squared for each of these operators. And if you work that out, you get the same thing. You get the same eigenvalue. So this is still consistent with what we found before. And then similarly, because the states, these ones, 1, 0 and 1 minus 1 have the same eigenvalue have the same total angular momentum, they will work out the same way. So again, you'll get alpha h bar squared over 4 for those two states. And this time, if we calculate the eigenvalue of our 0, 0 state using this new, the correct eigenvalues, you will find what we found before, that you get minus 3 alpha h bar squared over 4. So again, the point of all this is that now that we know the eigenstates of this Hamiltonian ahead of time, and we know the eigenvalues, we can just write down immediately our solution by applying the time evolution operator to our state, expanded in terms of these kets. And the only nuance to all of this is in calculating these eigenvalues directly from this operator, you have to know that they act in kind of a peculiar way, or the eigenvalues are not exactly what you would expect from these operators.